Okay, hi guys. So we'll be continuing on seeing the radioactivities, and this lecture's topic would be specific activity. So let's get started. But before going to that, let me write one more unit of activity. So we were seeing in the last lecture units of activity, wherein I forgot to tell one more unit, which was other. This is the third point or the third unit. So this is 1 RD or 1 Rutherford, which is equals to 10 raised to the power 6 disintegrations per second. Okay, now let's see specific activity. So specific activity is the activity per unit mass or activity of 1 gram of radioactive substance. So activity per unit mass or activity of 1 gram of radioactive substance or radioactive sample is called specific activity. Okay, now let's see the derivation of the same. So we'll now see the derivation. So we had dn by n is equals to lambda dt. Okay, I'm just shifting the lambda n to the left hand side and dt to the right hand side, and then let us integrate it. So we can write that number of nuclei after time t, nuclei of A after time t, can be written as n is equals to n naught times e to the power minus lambda t. So this is the value of n. Okay, so here with lambda can be written as 1 upon t ln n upon other n naught upon n, which can be written as 1 upon t ln of n naught upon n, which is the initial moles divided by number of moles of A at time t, which can also be written as 1 upon t ln w naught upon w. Okay, so the graph would look something like, on y-axis we have number of nuclei of A, and on x-axis we have time. So the graph would look like this. Okay, and some points here to note: that decay constant does not depend on temperature, and RNA's equations has no significance in radioactivity. In radioactivity. Okay, so we can also write from here lambda as we wrote that lambda would be equals to 1 upon t ln w naught upon w. So from here we can also write that lambda would be equals to ln 1 upon t ln w naught divided by w would be nothing but w naught minus x, where W is W naught minus X, where X is the amount which is already been disintegrated or decayed, and living amount would be W naught minus X. So just putting the value of W as W naught minus X in this equation. Okay, next let us discuss about half-life. So half-life is represented by T half. We have already seen this in our chemical kinetics chapter. So when T equals to T half, we can write that weight disintegrated or weight remaining would be equals to initial weight divided by 2. So we can write that T half would be equals to 1 upon lambda, just cross multiplying here, and this would be ln W naught upon what would be the value of X. Value of X would be W naught by 2. So W naught minus W naught by 2 would be W naught by 2. So this would be equals to 1 upon lambda ln 2. Okay, so this can be written as 0.693 upon lambda. This would be the half-life. So with this, we come to the end of this lecture. In the next lecture, we'll be seeing more on half-life, and then we'll also be seeing average life. So till then, good luck and goodbye.